There's something about the night sky above Sedona, Arizona, that makes theoretical physics feel less abstract. The town sits at an elevation of 4,350 feet in the high desert of northern Arizona, positioned in a way that creates exceptionally low light pollution for a populated area. In 2014, Sedona received recognition as an international dark sky community, a designation that requires strict lighting ordinances and community commitment to preserving natural darkness. On clear nights, particularly during the new moon phase, the Milky Way becomes visible as a dense band of light, containing an estimated 100 to 400 billion stars. And somewhere near the center of that galactic structure sits Sagittarius A, the supermassive black hole that holds the entire galaxy in gravitational orbit. The physics of black holes has traditionally been presented as a study of absolute endings, regions of space-time where gravity becomes so intense that not even light can escape once it crosses the boundary known as the event horizon. This understanding comes directly from solutions to Einstein's field equations, first published in 1915, which describe how mass and energy curve the fabric of space-time. Carl Schwarzschild was the first to find an exact solution to these equations in 1916, just months after the publication of General Relativity, describing what we now call a Schwarzschild black hole, a solution that predicts an event horizon at a specific radius depending on the object's mass. But Einstein's equations contain more information than this narrative of endings suggests. When Roy Kerr found a more realistic solution in 1963 for rotating black holes, the equations revealed more complex geometric structures, including the mathematical possibility of connected regions of spacetime, what physicists call Einstein-Rosen bridges or wormholes. These solutions aren't philosophical speculation. They emerge directly from the mathematics of general relativity when you solve the equations without making simplifying assumptions. The question isn't whether the mathematics allows these structures, but whether nature actually implements them. In Sedona, where dark skies permit direct observation of galactic structure without sophisticated equipment, this theoretical question takes on a different quality. The elevation and geographic location of the region, combined with municipal lighting policies, create conditions where amateur astronomers regularly observe phenomena that would require specialized equipment in areas with more light pollution. The Lowell Observatory, located approximately 28 miles north in Flagstaff, has utilized these atmospheric conditions since 1894, when Percival Lowell chose the location specifically for the clarity of the high desert air and atmospheric stability. The idea that black holes might function as passages rather than terminations isn't new in theoretical physics, but it remains in an area where mathematics is ahead of observational capacity. Physicists like Kip Thorne have extensively explored the conditions under which wormholes could exist and remain stable enough to permit passage, work that eventually contributed to his 2017 Nobel Prize in Physics for contributions to gravitational wave detection. The detection of these waves by LIGO in 2015 confirmed general relativity's predictions about colliding black holes, but still hasn't provided direct evidence about the internal structure beyond the event horizon. Tonight, as you settle into rest, we're going to explore the physics of black holes through a perspective that balances scientific rigor with contemplative accessibility. The goal isn't to master complex equations, but to understand the fundamental concepts that lead theoretical physicists to seriously consider the possibility that black holes might be connecting structures rather than absolute endpoints. We'll move through this exploration gradually, allowing each concept to settle before building upon it. The connection to Sedona isn't merely geographic. The region offers a concrete example of how specific conditions, in this case low light pollution and high elevation, enable observations that would be impossible in other contexts. Similarly, Black hole physics requires extreme conditions, intense gravity beyond anything we experience on Earth, to reveal properties of spacetime that remain hidden in more modest gravitational environments. There's a methodological parallel here. Just as dark skies reveal galactic structures invisible under artificial lighting, extreme gravitational conditions reveal geometric properties of spacetime invisible in weak gravitational fields. The structure we'll follow moves from the conceptual to the mathematical and back to the observational. We'll begin by examining what it means for spacetime to be curved, not as metaphor, but as literal description of the universe's geometry. Then we'll explore how extreme curvature creates event horizons and what the mathematics predicts about regions beyond those horizons. Subsequently, we'll consider the implications of wormhole solutions and what quantum physics adds to this picture. Finally, we'll examine what current observations can tell us and what remains beyond our present observational capacity. This format is designed specifically for nighttime listening. The scientific progression is real and rigorous, but the pace is gentle, allowing your mind to absorb concepts without strain. There's no test at the end, no need to memorize equations or technical details. The goal is to offer intellectual companionship as you transition towards sleep, providing enough substance to engage your curiosity without creating the anxiety that can accompany dense technical material. The physics we'll explore represents decades of theoretical and observational work by thousands of physicists around the world. It's knowledge built incrementally through careful observation, rigorous experimentation, and detailed mathematical analysis. At the same time, it remains incomplete, with fundamental questions still unanswered. This combination of solid knowledge and genuine mystery is part of what makes black hole physics appropriate for nocturnal contemplation. It offers both understanding and wonder, both answers and questions that remain open. If you're finding value in this exploration of black hole physics, this gentle journey through concepts that sit at the boundary between what we know and what we're still discovering, you're welcome to stay as long as you'd like. This channel exists to create exactly this kind of space, where scientific rigor meets restful contemplation, where the largest questions in physics can be approached without pressure or anxiety. If this resonates with you, consider subscribing so you can find more of these nocturnal explorations of cosmology, physics, and the structure of reality. And if you know someone else who finds comfort in scientific thinking during the quiet hours, sharing this might offer them the same companionship it's offering you tonight. But mostly, just settle in. The journey continues. Let's begin with the fundamental geometry of spacetime, because understanding black holes as potential doorways requires first understanding that space and time aren't separate entities, but components of a single four-dimensional structure. This concept, central to Einstein's general relativity, represents one of the most significant shifts in human understanding of physical reality. Before Einstein, physicists treated space as a fixed stage where events occurred, and time as a universal clock ticking at the same rate for all observers. Newton's physics worked perfectly well under this assumption for most practical purposes, and it took extraordinarily precise measurements to reveal that this framework was incomplete. The Michelson-Morley experiment of 1887, conducted to detect Earth's motion through the hypothetical luminiferous ether, instead revealed that the speed of light remains constant regardless of the observer's motion. This experimental result was incompatible with Newtonian mechanics and led Einstein to develop special relativity in 1905, which showed that space and time measurements depend on the relative motion between observer and observed. A decade later, general relativity extended this insight to include gravity, revealing that massive objects don't pull on other objects through some mysterious force acting at a distance, but rather curve the geometry of space-time itself, and objects moving through that curved geometry follow paths that appear to us as gravitational attraction. The mathematical description of this curvature uses tensor calculus, a branch of mathematics that generalizes vectors to higher dimensions and allows physicists to describe how geometry changes from point to point in spacetime. The Einstein field equations, often written in compact form as G mean Schurgassens 8pt Eman, relate the curvature of spacetime, represented by the Einstein tensor G Eman, to the distribution of matter and energy, represented by the stress-energy tensor T Eman. These equations are deceptively simple in their compact form, but expand into a system of 10 coupled, non-linear, partial differential equations that are notoriously difficult to solve except in special cases with high symmetry. The Schwarzschild solution, found by Karl Schwarzschild in 1916 while serving in the German army during World War I, represents the simplest exact solution to Einstein's equations, a non-rotating, spherically symmetric mass distribution. Schwarzschild's solution revealed something unexpected. There exists a critical radius, now called the Schwarzschild radius, at which the geometry of spacetime becomes so severely warped that the roles of space and time effectively swap. Inside this radius, the radial direction toward the center becomes time-like rather than space-like, meaning that falling inward becomes as inevitable as moving forward in time is for us in normal space-time. This radius defines the event horizon. For a non-rotating black hole, the Schwarzschild radius is given by Rs 2gm(c2), where g is the gravitational constant, m is the mass of the object, and c is the speed of light. For an object with the mass of our Sun, approximately 2 × 1030 kilograms, this radius works out to about 3 kilometers. The Sun's actual radius is about 696,000 kilometers, so it would need to be compressed by a factor of more than 200,000 to become a black hole. For Earth, with a mass of about 6 × 1024 kilograms, the Schwarzschild radius is approximately 9 millimeters. These calculations illustrate why black holes only form under extreme conditions. You need either enormous mass or incredible compression. The observational evidence for black holes has accumulated steadily since the 1960s. Cygnus X1, discovered in 1964 as a strong X-ray source, was the first widely accepted black hole candidate, identified through the orbital dynamics of its companion star HDE 226868. The mass of the unseen companion, estimated from the orbital parameters, exceeded the theoretical maximum mass for a neutron star, leaving a black hole as the only plausible explanation within known physics. Since then, astronomers have identified numerous stellar mass black hole candidates through similar techniques, looking for compact objects whose mass exceeds approximately 3 solar masses. The Tolman-Oppenheimer-Volkoff limit, beyond which neutron degeneracy pressure cannot support a stellar remnant. Supermassive black holes, with masses ranging from millions to billions of solar masses, have been identified at the centers of most galaxies through observations of stellar orbits and gas dynamics in galactic cores. The supermassive black hole at the center of our own Milky Way, Sagittarius A, has a mass of approximately 4.1 million solar masses confined within a region smaller than Mercury's orbit around the Sun. Andrea Ghez and Reinhard Genzel received the 2020 Nobel Prize in Physics for their decades-long observations of stellar orbits around Sagittarius A, providing compelling evidence for this concentrated mass. On clear nights in Sedona, when you look toward the constellation Sagittarius low on the southern horizon during summer months, you're looking toward the galactic center where this supermassive black hole resides, though the black hole itself is completely invisible, surrounded by clouds of gas and dust that block visible light. The 2019 Event Horizon Telescope image of the supermassive black hole in galaxy M87 provided the first direct visual evidence of an event horizon, showing a dark central region surrounded by a bright ring of emission from infalling matter heated to billions of degrees. This image, assembled from radio telescope observations at 1.3 millimeter wavelength coordinated across the globe, matched predictions from general relativity with remarkable precision. The shadow cast by the event horizon against the background of hot gas appeared exactly where the mathematics said it should, with a diameter of about 42 microarc seconds as seen from Earth, corresponding to a physical size of about 38 billion kilometers. Now, here's where the doorway concept begins to emerge from the mathematics. The Schwarzschild solution, when analyzed carefully, doesn't just describe a region of inward collapsing spacetime. The complete mathematical structure, called the maximal extension of the Schwarzschild geometry, includes four distinct regions: the exterior universe we inhabit, the black hole interior where we'd fall inward if we crossed the horizon, a white hole interior from which matter can only emerge, and another exterior universe connected to our own through the Einstein-Rosen bridge. This complete solution was first fully analyzed by Martin Kruskal and George Sikares independently in 1960, revealing geometric structures hidden in Schwarzschild's original solution. The Kruskal-Sikares coordinates provide a way to visualize the entire space-time structure without the coordinate singularities that appear in the standard Schwarzschild coordinates at the event horizon. In these coordinates, the wormhole nature of the geometry becomes apparent. There's a bridge connecting two asymptotically flat regions of space-time, two separate universes or two distant regions of the same universe. However, this bridge is dynamic, not static. It expands from zero size to a maximum and then collapses back to zero in a finite amount of proper time. And this expansion and collapse happen so quickly that nothing, not even light, can traverse the bridge from one exterior region to the other before it collapses. The wormhole exists mathematically, but is not traversable in the Schwarzschild case. Your breathing has perhaps slowed as you've followed this progression from basic geometry through observational evidence to mathematical structures. The concepts are substantial, but they don't require tension to hold. They can simply be there, like the dark sky over Sedona is there, vast and detailed and patient. We'll continue building on these foundations, moving toward the question of whether these mathematical bridges might, under different conditions, remain open long enough to permit passage. For now, let your mind rest with the image of space-time as geometry, curved and folded by mass, creating structures far stranger than our everyday experience suggests. The limitation of the Schwarzschild solution, that its wormhole cannot be traversed, led physicists to investigate whether more realistic black hole solutions might permit passage. The key insight came from recognizing that real astrophysical black holes don't match Schwarzschild's idealized assumptions. Real black holes form from collapsing matter, they rotate, and they exist in universes that contain other matter and energy. The Kerr solution, discovered by Roy Kerr in 1963, describes rotating black holes and reveals significantly different geometric structures that might, under certain interpretations, allow for more complex connectivity patterns in spacetime. A rotating black hole possesses angular momentum, a quantity conserved from the rotation of the star that collapsed to form it. This rotation fundamentally changes the geometry compared to the Schwarzschild case. Instead of a single event horizon, the Kerr solution predicts two horizons, an outer event horizon and an inner Cauchy horizon. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around the black hole in the direction of rotation, a phenomenon called frame dragging. In this region, it becomes impossible to remain stationary relative to distant stars. You're compelled to orbit the black hole even if you fire your rockets in the opposite direction, though you can still escape outward if you have sufficient velocity. The mathematical structure of the maximal extension of the Kerr geometry is even more complex than Schwarzschild's. The complete solution contains an infinite sequence of universes connected through the black hole's interior, like beads on a string. Passing through the ring singularity at the black hole's center in the Kerr geometry might theoretically transport you to another universe in this infinite sequence. However, the Corky horizon represents a boundary beyond which predictability breaks down. Classical general relativity cannot uniquely determine what happens past this boundary, even with complete knowledge of initial conditions. This suggests that quantum effects not included in classical general relativity become essential in these regions. The stability of these inner structures remains an open question in theoretical physics. Perturbation analyses suggest that the Corky horizon might be unstable, that any small amount of matter or energy falling into the black hole would cause the geometry at the Corky horizon to become singular, potentially destroying the bridge structure. This was analyzed in detail by Eric Poisson and Werner Israel in the 1990s, who showed that the mass inflation instability causes exponential growth of energy density at the inner horizon. If this analysis is correct, the exotic connectivity patterns predicted by the maximal Kerr solution might not survive in realistic astrophysical black holes. But the mathematics also allows for another class of solutions: traversable wormholes held open by exotic matter. In 1988, Kip Thorne and his student Mike Morris published a detailed analysis of what properties matter would need to have to keep a wormhole open long enough for something to pass through. Their conclusion was precise. You need matter with negative energy density, as measured by at least some observers. This violates the weak energy condition, one of several energy conditions that physicists generally assume matter must satisfy. Normal matter, everything we've ever directly observed, has positive energy density in all reference frames. However, quantum field theory permits violations of energy conditions under specific circumstances. The Casimir effect, experimentally verified in 1997 by Steve Lamoureux, demonstrates that quantum vacuum fluctuations can produce negative energy density between conducting plates. The Hawking radiation process, which we'll discuss more shortly, also involves negative energy falling into the black hole, while positive energy radiates away. These quantum effects suggest that the energy conditions might not be absolute prohibitions, but rather classical approximations that break down at quantum scales. Whether these quantum violations could be amplified to macroscopic scales sufficient to stabilize a traversable wormhole remains unknown. The quantities of exotic matter required to hold open a wormhole are extraordinary. For a wormhole with a throat radius of 1 meter, Thorne and Morris calculated that you'd need a total amount of negative energy roughly equivalent to the total positive mass energy of Jupiter, distributed in a specific configuration. Scaling this up to astrophysical-sized wormholes, the required exotic matter would exceed the mass of stars. No known mechanism can produce such quantities of negative energy, and fundamental questions remain about whether such configurations are even possible in quantum field theory, let alone achievable through any physical process. Stephen Hawking's analysis of black hole thermodynamics introduced another critical perspective on black hole interiors. In 1974, Hawking demonstrated that quantum effects near the event horizon cause black holes to emit thermal radiation, now called Hawking radiation, with a temperature inversely proportional to the black hole's mass. For a solar mass black hole, this temperature is approximately 60 nanokelvins, far colder than the cosmic microwave background radiation that permeates space at 2.7 Kelvin. This means stellar mass and supermassive black holes are currently absorbing more energy from the cosmic background than they emit through Hawking radiation, so they're slowly growing. However, as the universe continues expanding and cooling, and as the cosmic background temperature eventually drops below the Hawking temperature, black holes will begin to slowly evaporate. The timescale for black hole evaporation is immense beyond human comprehension. A solar mass black hole would take approximately 1067 years to evaporate completely through Hawking radiation, a duration incomprehensibly longer than the current age of the universe at 13.8 billion years. For supermassive black holes like the one at the center of M87, with a mass of about 6.5 billion solar masses, the evaporation time extends to roughly 10 to 100 years. These timescales are so vast that they exceed the proton decay timescale predicted by some grand unified theories, meaning black holes might outlive ordinary matter itself. The Hawking radiation process raises profound questions about information conservation in quantum mechanics. Quantum mechanics requires that information about a system's quantum state be preserved over time, a principle called unitarity. But if a black hole forms from matter with specific quantum states, then evaporates completely through thermal radiation that carries no information about those initial states, the information appears to be destroyed. This black hole information paradox has occupied theoretical physicists since the 1970s and remains one of the deepest unresolved questions at the intersection of quantum mechanics and general relativity. Several proposed resolutions to the information paradox have implications for the doorway concept. One proposal suggests that information is encoded in subtle correlations in the Hawking radiation itself, though the mechanism for this encoding remains unclear. Another possibility is that information is preserved in remnants, stable or metastable objects with roughly the Planck mass that remain after evaporation completes. A third category of proposals suggests that information might escape through the wormhole connection, if one exists, preserved in whatever region the wormhole connects to, rather than being radiated back into our universe. Recent developments in theoretical physics have introduced new perspectives on black hole interiors. The holographic principle, emerging from work by Gerard 't Hooft and Leonard Susskind in the 1990s, suggests that all the information contained in a volume of space can be encoded on the boundary of that region, like a hologram encodes three-dimensional information on a two-dimensional surface. Applied to black holes, this principle suggests that the interior might not contain independent information beyond what's encoded on the event horizon itself. This raises deep questions about what interior even means in this context, and whether the geometric picture of wormholes connecting regions is the right way to think about black hole structure. In Sedona's dark skies, when you observe the Milky Way's central region, you're looking towards Sagittarius AC across approximately 26,000 light-years of space. The photons reaching your eyes left that region 26,000 years ago, when anatomically modern humans were just beginning to create cave paintings in Europe. Those photons carry information about the matter and radiation near the galactic center, but they reveal nothing about the black hole's interior beyond the event horizon. Everything that happens inside remains fundamentally inaccessible to external observation, protected by the horizon. This observational barrier is both a frustration and a frontier. It marks the boundary between what we can measure and what we must infer through theoretical reasoning. The mathematics suggests doorways, connections, bridges through spacetime. But mathematics alone cannot tell us what nature implements. That requires observation, experiment, measurement, and so we're left with this careful balance, taking seriously what the equations predict while acknowledging the enormous gap between mathematical possibility and physical actuality. Let your mind rest in that balance. in the space between knowing and wondering as we prepare to explore what quantum mechanics adds to this picture. Quantum mechanics introduces a fundamental indeterminacy into physics that profoundly affects how we think about black hole interiors. The Heisenberg uncertainty principle establishes that certain pairs of physical properties cannot simultaneously have definite values. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of measurement technology, but a fundamental feature of quantum reality. Applied to the extreme conditions near and inside black hole event horizons, quantum uncertainty becomes impossible to ignore, suggesting that the classical picture of smooth spacetime geometry might break down precisely where it becomes most curved. The scale at which quantum gravitational effects become dominant is set by the Planck length, approximately 1.6 kicks 10 to 35 meters, derived by combining the gravitational constant, the speed of light, and Planck's constant. At this scale, the quantum fluctuations of spacetime itself become comparable to its classical curvature. The Planck length is unimaginably small. If you expanded a proton to the size of the observable universe, the Planck length would only grow to about the size of a large tree. Yet it represents a fundamental limit on how finely we can probe spacetime structure before our current physical theories cease to give meaningful predictions. Near a black hole's singularity, where classical general relativity predicts infinite curvature and infinite density, quantum effects must become important. The singularity itself might not exist as a geometric point, but rather be replaced by some quantum structure whose properties we cannot yet calculate, because we lack a complete theory of quantum gravity. Several approaches to quantum gravity suggest different pictures of what might replace the classical singularity. Loop quantum gravity suggests a quantum bounce, where collapsing matter reaches a maximum density and then begins expanding again, potentially creating a new region of spacetime on the other side of what classically would be the singularity. This bounce mechanism comes from the discreteness of space in loop quantum gravity. In this approach, spacetime is not infinitely divisible, but is made of discrete quanta, of area and volume, much like matter is made of discrete atoms rather than being a continuous fluid. When matter collapses in this discrete geometry, it cannot compress beyond a certain maximum density because there is a minimum volume that each quantum of space can have. Once this maximum density is reached, the quantum pressure becomes repulsive rather than attractive, causing the collapse to reverse into expansion. If this picture is correct, the matter falling into a black hole would be compressed to this maximum quantum density and then expelled into a new region of spacetime, potentially emerging as what we'd observe as a white hole if we could see it. This scenario provides a physical mechanism for the mathematical bridge structure that appeared in the classical solutions. The bridge isn't held open by exotic matter with negative energy density, but rather is traversed so quickly in proper time during the quantum bounce that the question of stability becomes different. The passage exists for the duration of the bounce, measured in units of Planck time, approximately 5.4 x 10^44 seconds. Another approach to quantum gravity, string theory, suggests different structures for black hole interiors. In string theory, fundamental particles are not point-like, but are one-dimensional strings, whose vibration modes correspond to different particle types. At high enough energies, near the Planck scale, these strings can exist in extended, fuzzy configurations that don't have precise locations. Applying string theory to black holes has led to the concept of fuzzballs, where the black hole interior is replaced by a horizon-sized quantum structure with no interior or singularity at all. In this picture, the black hole is entirely the horizon. There's nothing inside to connect to anything else. The tension between these different approaches reflects our fundamental uncertainty about how to unify quantum mechanics and general relativity. Both theories are extraordinarily successful in their domains. Quantum mechanics describes the physics of atoms, molecules, and subatomic particles with remarkable precision, while general relativity describes the large-scale structure of spacetime, from planetary orbits to the expansion of the universe itself. But where both effects become important simultaneously, at the Planck scale or in black hole interiors, we lack experimental guidance to choose between competing theoretical frameworks. Hawking's calculation of black hole radiation provides one of the few semi-solid results where quantum mechanics and gravity meet. The calculation uses quantum field theory in curved spacetime, treating the spacetime geometry as classical and fixed while allowing the quantum fields to fluctuate. Near the event horizon, quantum fluctuations can create particle-antiparticle pairs from the vacuum, and occasionally one particle falls into the black hole while the other escapes to infinity. The infalling particle carries negative energy from the perspective of an external observer, causing the black hole to lose mass, while the escaping particle forms the Hawking radiation. This process has never been directly observed for astrophysical black holes because the radiation is so faint compared to other sources. However, analogous processes have been demonstrated in laboratory analogues called dumb holes, or acoustic black holes. These are fluid systems where the flow velocity exceeds the speed of sound in the fluid, creating an acoustic event horizon from which sound waves cannot escape. William Unruh proposed this analogue in 1981, and experimental realizations using Bose-Einstein condensates have demonstrated spontaneous emission of phonons from the acoustic horizon, analogous to Hawking radiation. The connection between black hole physics and quantum information theory has become increasingly important in recent decades. Quantum information, measured in qubits, has properties that classical information doesn't have, particularly quantum entanglement, where measurements on one system instantaneously affect measurements on another system regardless of the distance between them. When one member of an entangled pair falls into a black hole while the other remains outside, the entanglement creates correlations across the event horizon. Understanding how this entanglement evolves as the black hole evaporates has led to new insights into the structure of spacetime itself. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests a deep connection between Einstein-Rosen bridges, wormholes, and quantum entanglement. In this framework, entangled particles are connected by microscopic wormholes, too small and short-lived to permit classical information transfer, but representing a genuine geometric connection. If this conjecture is correct, then quantum entanglement isn't just correlation at a distance, but is mediated by actual, if non-traversable, spacetime geometry. This would mean that wormholes aren't exotic structures requiring special conditions, but are ubiquitous features of spacetime geometry, present wherever quantum entanglement exists. Applied to black holes, ER-EPR suggests that the horizon might be laced with microscopic wormholes, connecting the black hole interior to the exterior through quantum entanglement. These connections wouldn't allow escape from inside the event horizon, but they might provide a mechanism for information to be preserved and eventually encoded in the Hawking radiation. The interior wouldn't be completely cut off from the exterior, but would remain connected through quantum geometric structures that classical general relativity cannot describe. These ideas remain speculative, living at the frontier where experimental confirmation is not yet possible. We cannot probe Planck-scale physics directly with current technology. The energies required exceed anything achievable in particle accelerators by many orders of magnitude. We cannot observe black hole interiors. The event horizon prevents any signals from escaping. We must instead rely on theoretical consistency, mathematical elegance, and indirect observational tests. This places black hole interior physics in a unique position. It's a domain where nature implements physics we can theorize about, but cannot yet directly observe. In the high desert silence around Sedona, where the night sky permits direct observation of cosmic structure with minimal interference, there's a useful parallel to the theoretical situation. You can observe the stars, the galaxies, the large-scale structure of the universe. But the physics happening at the Planck scale inside black holes is as invisible to you as individual atoms were to ancient Greek philosophers who theorized about atomism without any way to directly observe atoms. Yet both the ancient atomists and modern quantum gravity theorists are engaged in the same fundamental activity, using reason, mathematics, and consistency arguments to infer the structure of a reality that sits just beyond the current reach of direct observation. Sometimes that reach extends over time. Atoms became observable with the right instruments. Whether black hole interiors will ever become directly observable remains an open question. The question of whether black holes function as doorways cannot be separated from the question of what it means for something to exist. This might seem like philosophy rather than physics, but at the boundary of a black hole's event horizon, the distinction becomes less clear than academic departments suggest. General relativity tells us that space-time structure is observer-dependent, different observers moving relative to each other or positioned at different gravitational depths measure different intervals of time and space between the same events. This observer dependence extends to questions about event horizons in ways that bear directly on the doorway concept. Consider what happens from different perspectives as an object approaches and crosses an event horizon. An observer remaining far from the black hole at a safe distance where gravity is weak sees the infalling object slow down as it approaches the horizon. Due to gravitational time dilation, clocks closer to the event horizon run slower as measured by the distant observer. As the object gets closer and closer to the horizon, it appears to slow more and more, with light from the object becoming increasingly redshifted as the photons climb out of the deepening gravitational well. The distant observer never actually sees the object cross the horizon. It appears to freeze asymptotically approaching the boundary, fading to invisibility as the redshift becomes infinite. But from the perspective of someone falling with the object, the experience is entirely different. Their clock runs at its normal rate from their perspective, and they cross the event horizon in a finite amount of proper time, perhaps not even noticing the exact moment of crossing. There's no local marker at the horizon, no wall or barrier, just a mathematical surface defined by being the point of no return. After crossing, they continue falling inward toward the singularity, experiencing increasing tidal forces as the gravitational gradient becomes more extreme. From their perspective, they definitively cross the horizon and enter the black hole interior, while the distant observer sees them perpetually frozen just outside. Both descriptions are correct within their reference frames. General relativity doesn't privilege one perspective over the other. It provides mathematical tools to translate between different observers' descriptions, and those descriptions agree on all measurable outcomes, even though they disagree on questions like, has the object crossed the horizon yet? This relativity of simultaneity, extended to the extreme environment of black holes, means that whether something is inside or outside the horizon depends on who's asking. The concept of complementarity in quantum mechanics adds another layer to this perspective dependence. In quantum complementarity, different experimental setups reveal complementary aspects of reality that cannot be simultaneously observed. The classic example is wave-particle duality, where experiments designed to detect wave properties see waves, and experiments designed to detect particle properties see particles, but no single experiment can reveal both aspects simultaneously. Applied to black holes, complementarity suggests that the description of an object's information being absorbed into a black hole and the description of that information being encoded on the event horizon and eventually radiated back out might both be valid complementary descriptions rather than contradictory alternatives. Leonard Susskind developed this idea into the black hole complementarity principle in 1993, arguing that an infalling observer sees the information they carry cross the horizon and fall toward the singularity, while an external observer sees that same information thermalized and eventually re-emitted in Hawking radiation. These descriptions seem contradictory. How can the information both fall into the singularity and be radiated back out? But Susskind argues they describe the same physics from complementary perspectives, neither of which can be checked against the other, because no observer can be both inside and outside the horizon simultaneously. This raises questions about the nature of the black hole interior. If everything an external observer needs to know about a black hole is encoded on its event horizon, and if the interior is only accessible to observers who can never communicate back outside, then in what sense does the interior exist for those of us who remain outside? This isn't solipsism or denial of external reality. It's recognizing that in a theory where space-time geometry depends on observer state, the question, what exists, may not have a single universal answer independent of who's asking. The holographic principle, mentioned earlier, takes this idea to its logical conclusion. If all the information about a volume can be encoded on its boundary, then perhaps the fundamental description of physics is always in terms of boundary data, and interior bulk spacetime is a derived, emergent description useful for certain calculations, but not fundamentally real. Applied to the universe as a whole, this suggests that our three-dimensional space might be a holographic projection of information encoded on a distant two-dimensional boundary, perhaps at the edge of the observable universe. These ideas connect to the doorway concept in a subtle way. If the black hole interior is a complementary description of the same physics that's described from the outside as information on the horizon, then asking whether there's a wormhole connecting through the interior might be asking the wrong question. The wormhole might be a feature of the interior description that doesn't have a direct counterpart in the boundary description. Or following ER-EPR, the wormhole might correspond to quantum entanglement in the boundary description, making it real in a quantum geometric sense, but not traversable in the classical sense of sending signals through it. Observational evidence for these ideas remains indirect. We can observe matter falling toward black holes. We can measure the spin and mass of black holes from their effects on nearby matter. And we've now directly imaged the event horizon shadow of supermassive black holes. But we cannot observe the interior beyond the horizon, cannot detect Hawking radiation from astrophysical black holes, cannot probe Planck-scale structures, and cannot confirm whether wormholes exist inside black holes. The evidence we have confirms general relativity's predictions about event horizons existing at the predicted locations, but it's silent on the deeper questions about interior structure. The LIGO and Virgo gravitational wave detectors have added new observational tools to black hole physics since their first detection in 2015. When black holes merge, they create ripples in spacetime that propagate outward at the speed of light, carrying information about the mass's spins and orbital dynamics of the merging objects. The ring-down phase after merger, when the merged black hole settles into a stable configuration, provides information about the final black hole's properties that can be compared with general relativity's predictions. So far, all observations match general relativity with remarkable precision, providing no evidence for deviations that might hint at exotic interior structures. But the ring-down phase tests the exterior space-time geometry, not the interior beyond the horizon. The gravitational waves are emitted from the curved space-time outside the event horizon as the geometry settles into the Kerr solution. They carry no direct information about whether there's a wormhole inside, whether there's a quantum bounce instead of a singularity, or whether the holographic principle means the interior is emergent rather than fundamental. These questions remain beyond current observational reach. Future observations might provide indirect tests. If black holes lose mass through Hawking radiation over incredibly long timescales, the spectrum and correlations in that radiation might encode information about the evaporation process and whether information is preserved. If primordial black holes formed in the early universe with low enough mass, they might be evaporating today, potentially producing detectable signals. If traversable wormholes exist naturally or could be created, they might be detectable through their gravitational effects on nearby matter. But all of these possibilities require either waiting timescales far longer than human civilization has existed, or developing technology far beyond current capabilities. In the observable silence of a Sedona night, where patient darkness permits contemplation of structures billions of light-years away, there's a useful reminder about the relationship between observation and theory. We observe what instruments and geometry allow us to observe. Theory extends beyond observation, using mathematics to explore regions we cannot access. Sometimes observation catches up. Atoms, once purely theoretical, became observable. Sometimes it doesn't. The interior of the sun remains unobservable by direct light, but we infer its structure through neutrino detection and solar models. Black hole interiors might remain permanently beyond direct observation, or they might become accessible through methods we haven't yet imagined. The honest answer is, we don't know. Let's return to the specific question that frames this exploration. Might black holes be doors rather than endings? We've moved through the geometry of curved space-time, the mathematics of event horizons and wormholes, the quantum effects that complicate classical descriptions, and the observational limitations that constrain what we can know. Now we can assemble these pieces into a careful answer that respects both what the physics suggests and what it leaves uncertain. The mathematics of general relativity definitively permits wormhole structures connecting distant regions of space-time through black hole interiors. This isn't speculation. It's directly present in exact solutions to Einstein's field equations, like the maximally extended Schwarzschild and Kerr geometries. The question isn't whether the mathematics allows it, but whether nature implements these mathematical possibilities under realistic astrophysical conditions. That question remains open. The classical wormholes in Schwarzschild and Kerr solutions are non-traversable. They collapse too quickly for anything to pass through before being crushed at the singularity. Making a wormhole traversable requires exotic matter with negative energy density to hold it open, and while quantum effects can produce negative energy densities in restricted circumstances, we don't know whether such effects can be scaled up to macroscopic levels or maintained in the configurations required for wormhole stabilization. Current physics doesn't forbid it, but neither does it provide a mechanism to achieve it. Quantum gravity effects might change this picture. If loop quantum gravity's prediction of a quantum bounce is correct, collapsing matter might not hit a singularity, but might instead reach a maximum density and then expand into a new region of space-time, potentially emerging as a white hole. This would provide a physical doorway through the black hole, but one that operates on Planck timescales and might not preserve macroscopic structure through the transition. An object falling in wouldn't emerge intact on the other side, but would be disassembled at the quantum level and reconstituted into whatever configuration the bounce dynamics produce. Alternatively, if string theory's fuzzball picture is correct, there might not be an interior at all, just a horizon-sized quantum structure with no doorway to anywhere. Or if the holographic principle indicates that interior geometry is emergent rather than fundamental, the question of whether wormholes exist inside might not have a definite answer, independent of which complementary description you're using. The interior description might include wormholes, while the boundary description describes the same physics entirely in terms of horizon data, with no mention of interior connections. The ER-EPR conjecture suggests that microscopic wormholes might be ubiquitous, present wherever quantum entanglement exists, but these microscopic geometric connections wouldn't permit classical information transfer or travel. They'd represent a different kind of connection, quantum geometric rather than classically traversable. This would make wormholes real and present throughout space-time, but not functional as doors, in the conventional sense of things passing through them. What can we say with confidence? Black holes definitely exist. The observational evidence is overwhelming. Event horizons exist at the locations predicted by general relativity. The Event Horizon Telescope images confirm this. The interiors beyond those horizons definitely exist for infalling observers who cross them, though those interiors remain forever inaccessible to external observers. Quantum effects become important somewhere in the black hole interior, though exactly where and how remains uncertain. And the mathematics allows for connectivity structures that could constitute doors under the right conditions. What remains uncertain? Whether realistic astrophysical black holes contain traversable wormholes, whether quantum gravity replaces singularities with bounces that create new regions of space-time, whether information that falls into black holes remains in our universe or transfers elsewhere, whether black hole interiors are fundamental or emergent, whether the mathematical wormhole solutions correspond to anything physically real or are merely artifacts of extending the mathematics beyond its domain of applicability. These uncertainties aren't failures of physics, but rather honest acknowledgements of the boundaries of current knowledge. Physics proceeds by careful observation, mathematical analysis, and theoretical reasoning, and sometimes those tools take us to questions we cannot yet answer. The appropriate response isn't to pretend we know more than we do, or to dismiss questions as meaningless because they're hard to test, but rather to hold them carefully, distinguishing what we've established from what remains open. For someone listening to this in the quiet hours, perhaps in Sedona under dark skies that reveal the Milky Way's structure, or perhaps somewhere else entirely, the value of this exploration isn't in arriving at definitive answers, but in seeing how physics approaches questions at the edge of knowledge. The method remains consistent. Start with observation. Build mathematical models that describe what you observe. Use those models to make predictions. Test the predictions. Refine the models. When you reach questions that current observations cannot answer, you extend the mathematics carefully, exploring what different theoretical frameworks predict, looking for ways to distinguish between possibilities. The question of black holes as doors sits at this frontier. The mathematics suggests possibilities. Observation confirms some predictions while leaving others untestable. And theoretical physics continues working to develop frameworks that might eventually resolve the open questions. Whether those questions will be answered through future observations, through breakthrough theoretical insights, or through some combination we cannot yet anticipate, remains to be seen. There's something appropriate about this uncertainty residing in black holes, the most extreme objects in the known universe. They sit at the intersection of general relativity's description of gravity as geometry, quantum mechanics' description of matter and energy at small scales, and thermodynamics' description of entropy and information. A complete understanding of black holes likely requires a complete theory of quantum gravity, something physicists have been pursuing for decades without full success. Black holes are nature's laboratories for physics beyond the standard model and general relativity, regions where we know our current theories are incomplete but cannot yet observe what completes them. The night sky above Sedona provides a useful perspective on this situation. When you observe the galactic center in Sagittarius, you're seeing light from stars orbiting the supermassive black hole Sagittarius AI. That light left those stars 26,000 years ago, traveling across the galaxy to reach your eyes. The black hole itself is invisible, revealed only through its gravitational effects on visible matter. This has been the pattern throughout the history of astronomy. We observe effects, infer causes, develop models, make predictions, test them against new observations. Sometimes the cycle completes quickly, sometimes it takes centuries. Sometimes, as with black hole interiors, it might take longer than human civilization has existed. But the questions remain genuine questions, grounded in established physics and mathematics, not mere speculation. Whether black holes are doors depends on which of several mathematically consistent theoretical frameworks correctly describes quantum gravity, on whether exotic matter can exist in the required configurations, on whether information is preserved through black hole evaporation, on whether spacetime is fundamentally holographic. These are questions that theoretical physics can formulate precisely and, in principle, answer through a combination of theoretical development and observational testing. For now, in this moment, as your breathing slows and your mind prepares for sleep, you can rest with the knowledge that the universe contains structures stranger than everyday experience suggests, that mathematics provides tools to describe those structures even when we cannot directly observe them, and that the boundary between knowledge and mystery shifts over time as observation and theory advance. Black holes might be doors. They might be endings. They might be both from different perspectives, or the question itself might need reformulation in a future theory we haven't yet developed. All of these possibilities remain open, held carefully by a scientific community that continues to explore, calculate, observe, and refine our understanding of the cosmos we inhabit. The silence above Sedona holds a quality that connects directly to the physics we've explored tonight. In that high desert darkness, where municipal lighting ordinances preserve natural night skies and elevation reduces atmospheric interference, the visible structure of the Milky Way appears with clarity impossible in most populated areas. The dense band of stars, the dark dust lanes, the faint glow of nebulae all become apparent to patient eyes that allow time for adjustment to darkness. This darkness isn't empty. It's full, dense, with photons carrying information across cosmic distances, with neutrinos passing through Earth from the sun's core, with gravitational waves rippling through spacetime from distant mergers. Black holes, in their profound darkness, might offer a similar fullness rather than emptiness. The event horizon isn't a wall, but a boundary in space-time geometry, a point of no return from the perspective of external observers, but a traversable surface from the perspective of anyone falling through. Beyond that boundary, in regions forever inaccessible to external observation, space-time curvature becomes extreme, quantum effects become dominant, and our current physics reaches the limits of its predictive power. What exists there remains uncertain, held in the space between mathematical possibility and physical confirmation. The question of doorways through black holes connects to deeper questions about the nature of physical reality. Is space-time fundamental or emergent? Is information preserved universally, or can it be destroyed? Do quantum mechanical descriptions and space-time geometric descriptions represent different aspects of a single underlying reality or fundamentally different levels of description? These questions extend beyond black holes to the foundations of physics itself, and black holes, as the most extreme gravitational environments in the known universe, provide the context where these foundational questions become most acute. For you, settling into sleep in whatever location you've chosen for tonight's rest, these questions don't require resolution. They can simply exist, like the stars exist, present and magnificent, whether or not we understand their detailed physics. The value in exploring them isn't primarily in reaching answers, but in experiencing the process of scientific inquiry, seeing how physics approaches questions at the boundary of knowledge with careful reasoning, mathematical rigor, and appropriate epistemic humility about what remains uncertain. The red rock formations around Sedona, compressed and lifted and eroded over hundreds of millions of years, offer their own lesson about time and transformation. The Schnebly Hill sandstone, visible in Cathedral Rock and Bell Rock, formed from sediments deposited in ancient seas, compressed over time, later lifted by tectonic forces, and slowly carved by water and wind into the current formations. The iron oxides that give the rocks their characteristic red color represent oxygen released by early photosynthetic organisms billions of years ago, combined with iron from stellar nucleosynthesis in stars that exploded before the sun formed. The rocks are layered history, transformation made visible, endings that became new beginnings. Black holes might function similarly in cosmic history. Matter that collapses beyond an event horizon might not end, but might transform in ways we cannot yet observe or fully understand, potentially emerging in different space-time regions, potentially seeding new universes through mechanisms loop quantum gravity suggests, potentially being preserved in quantum information structures that transcend our classical geometric intuitions. Or they might indeed be endings, with information somehow preserved in subtle correlations in Hawking radiation emitted over timescales that dwarf the current age of the universe. The honest answer is that we don't yet know, and that uncertainty is appropriate to hold carefully rather than prematurely resolve through speculation beyond what the physics supports. As your consciousness drifts toward sleep, let these ideas settle without requiring you to grasp them tightly. The universe operates according to physical laws, whether or not any conscious being understands those laws. Stars form, burn, and die. Galaxies orbit their central black holes. Space-time curves in response to mass and energy. Quantum fields fluctuate in vacuum. All of this proceeds without needing our understanding, and yet we have the remarkable capacity to observe, to question, to build mathematical models, to test predictions, to gradually extend the boundary of what we comprehend. That capacity is itself a wonder worth contemplating as you drift into rest. Somewhere above Sedona tonight, if the sky is clear, the Milky Way arches overhead, its central bulge pointing toward Sagittarius, where the supermassive black hole resides, invisible but profound, holding 4.1 million solar masses in a region smaller than Mercury's orbit, existing as confirmed by decades of careful stellar orbit observations, remaining mysterious in its interior structure beyond the event horizon. That black hole might contain doorways to elsewhere. It might not. But it definitely exists, definitely curves space-time, as general relativity predicts, definitely represents physics at the edge of our current understanding. And that is sufficient for tonight, sufficient for this gentle exploration that accompanied you through the quiet hours. Rest well.